Nowadays, intelligent applications come from the deployment of machine learning models, which are trained by using massive data. This process often consumes heavy computing resources, and a conventional platform is centralized computing at the cloud server. Thanks to the increasing computing capacities, more powerful distributed devices can support partial computing tasks, and centralized training has been gradually replaced by the distributed computing platform. The centralized server first allocates the data to the device, and then each device computes the task locally. After local computing, the device uploads the results through wireless channel, and the local results help to build the global model at the server. The new article, Channel-Driven Monte Carlo Sampling for Bayes Distributed Learning in Wireless Data Centers, considers Bayes learning in the distributed computing platform. The first question is, why Bayes learning? We take a step back to look at frequency learning. Given the training dataset, frequency learning aims to obtain a single optimal point in the model parameter space, while in Bayes learning, the target is to compute the posterior distribution of model parameters given the training dataset, which contains more information than that in frequency learning. As a result, it can quantify epistemic uncertainty, the uncertainty in the model parameter space, and facilitate active learning and online learning. Also, it is robust to overfitting. In the distributed computing paradigm, we can further see the advantage of Bayes learning. In frequency learning, we have two local optimal points. Typically, what happens in frequency learning is that these 2 points are averaged at the server and give us a global estimate. However, this estimate is not good for any two devices because both of them attain zero posterior distribution. If we use Bayes learning, each device has its own posterior distribution, which is computed by the local dataset. In principle, we can simply multiply these two posteriors and get the global posterior, which clearly indicates that there are two parts in the space that are useful for both devices. So, Bayes learning gives us a principle to combine information from multiple sources. Ideally, in Bayes learning, given the entire dataset, the learner will obtain a posterior distribution in the model parameter space. In practice, to represent this distribution, we can draw samples from this distribution, that is, Monte Carlo sampling. With more samples, we get better representations of this distribution, but at the cost of computing and communication resources. For the downstream application, each sample corresponds to a different predictor, and you can average the predictions generated by the samples and quantify the disagreement among different predictors. When devices communicate the local posterior to the server, which is represented by these samples, is synergistic with communication on noisy channels, and we call it channel-driven Monte Carlo sampling. In the conventional digital communication where the transmitter aims to send a digital message, let's say 1 bit as an example, at the receiver side, the conditional distribution of the received sample should be separated enough such that the receiver can tell which bit was encoded by the transmitter. This is often tagged by the channel coding to mitigate the noise. The situation in Bayes learning is quite different. The transmitter wants to communicate the distribution to the receiver, more specifically the samples of the distribution. The receiver doesn't recover the digital bits, but hopes that the statistics of the received samples are as close as the true distribution. Intuitively, if we have the true distribution here and reshape it before transmission, then the received distribution, which has incorporated the channel noise, in some cases can perform exactly as the true distribution. This work considers both orthogonal multi-access channel and non-orthogonal multi-access channel. For a pre-coded sample theta k, which corresponds to the different local posteriors, the weight matrices are designed to approximate the true posterior distribution under the contamination of the channel noise. The contributions of this work include two parts. First, considering the local posteriors following Gaussian distribution. This work proposes an analytical approach that is asymptotically optimal. Then, to cope with an arbitrary distribution, it introduced a variational design that aims at reducing the KL divergence between the distributions of the aggregated samples and the true global posterior. We can see that the performance measured by the test error is less sensitive to the level of SNR, that is, the channel noise has no harm to the distributed Bayes learning. If you want to know more, I recommend you to read the paper Channel-Driven Monte Carlo Sampling for Bayes Distributed Learning in Wireless Data Centers, published in IEEE Journal on Selected Areas in Communications in 2022.